after a brief stint with some problem solving on geometrical optics, so we have this sheet on us, optics right there, and assuming you would have attempted a bunch of problems from the sheet already by this time, let's look at these problems together, right? So the first problem of the sheet is about a lens of focal length 30 centimeters. So along with sine minus 30 centimeters. And with an object O at a distance 36 centimeters, and there is a mirror placed 1 meter from the lens, inclined at 45 degrees. 1 meter from the lens, there is a mirror placed. Let's say CP. CP is 1 meter. CP is 1 meter. And it is found. And there is a tray of water here. There is a tray of water 85 centimeters from the principal axis, below the principal axis, the bottom of this, with a layer of water of thickness h centimeters. And the image of the object O formed out of a refraction from the lens and reflection from this mirror placed at 45 degrees, is formed at the bottom of the tray, We want to find the height of water in the tray, right? This is what we want to be able to do. Okay. So now the whole blueprint is there is an image formed by this lens, right? Now that image will serve as the virtual object for reflection on this mirror. It may be a real object also. It could be a virtual object as well. I mean, if the image of this is formed before the mirror, then it will be a real object for the plane mirror. Otherwise, that's good. If the image of the object O formed by this lens is to the right of the mirror, then that object actually never gets, that image actually never gets formed. That will serve as a virtual object for reflection in the mirror. Yes or no? Okay. So first things first, refraction from lens. Lens L. The image, let's say, is formed at a distance at V from the lens. So 1 by V, the image formed by the lens, right? 1 by V minus U in this direction. So plus 36 centimeters minus 1 by 36 is F, 1 by F minus 30, because focus, it's a converging lens, its focus will lie somewhere there. So focal length would be negative. So minus 1 by 30. This will give you the image formed by the lens if the mirror was not there. If the mirror was not there, this would give me 1 by V equal to 1 by 36 minus 1 by 30, which is 6 by 36 into 30 with a minus sign, 180. So V is minus 180 centimeters. V is minus 180 centimeters. Now what it really means is that the image of O would be formed 180 centimeters from the optical center of the lens. That means to the right of the mirror, right? But those rays of light which are seeking to get converged, this was the object O, and their image would have been, the image of this object would have been formed at I 180 centimeters, right? But what happens is there is a mirror 1 meter away from the lens. There is a mirror 180, right? 1 meter away from the lens. So this mirror intercepts this ray. This mirror would intercept this ray, and it would go reflection, it would undergo a reflection. So then for the reflection here, what is the object? I is the object. In this case, it's a virtual object. It's a virtual object because rays of light got prevented from actually converging to I. They got intercepted by the mirror here and underwent reflection. Okay, now what would have happened is the image of I would have been formed at some I prime. After reflection from the mirror, the image of I would have been formed at I prime. Now, how would it have been? If this was I, very clearly, I would have been 180 centimeters from the lens, means 80 centimeters from the mirror, right? So, this would have been 80 centimeters, and this is 45 degrees. The image of I, the virtual object, would be a real image. I1 would have been a real image. I1, right? And very clearly, again, this is 45 degrees. This is 45 degrees. These two triangles are congruent, object distance, image distance. So if this is 80, this is also 80. Yes or no? Which means, if this tray of water was not there, the image would have been formed after reflection 80 centimeters below the principal axis, right below this point. Yes or no? Do you understand that? But that was not to be. That was not to be. What happened was these rays of light, after reflection from the lens that are seeking to converge at some I1, got intercepted by this water surface, let's say one of the rays of light after reflection from the mirror that would have attempted to converge at I1, 80 centimeters below the principal axis, would undergo a deviation here because of refraction. Yes or no? It passes from a rarer to a denser medium. This is air, this is water, right? And H units of water, instead they converge to I2. Where I2 is 85 centimeters below the principal axis. It's formed at the bottom. I1 is 80 centimeters. I2, which is final image formed out of refraction from this water surface, is 85 centimeters. Now, that means the shift is 5 centimeters. The shift is 5 centimeters. The shift is 5 centimeters is caused by what? It's like a slab, a water slab of thickness h and refractive index 4/3. The shift that this is capable of causing is h, the thickness, into 1 minus 1 by mu is the shift that it causes, which is 5 centimeters. Yes or no? This h units will cause a shift of 5 centimeters, which is h into 1 minus 1 by mu of water. Yes or no? Right? So h, which is what we are seeking to find, into 1 minus 1 by mu. Mu of water is 4/3. That must be equal to the shift, which is 5 centimeters, as you can see. 5 centimeters. So 3/4, h is 20 centimeters. Yes or no? Do you all understand this? This is a ray of light. One of the rays getting reflected from the mirror, seeking to converge at I1, but because of this water surface, it shifts by an amount 5 centimeters. The shift caused by h units of a water slab of refractive index mu is h into 1 minus 1 by mu, which is clearly 5 centimeters. This length and this length enjoy a real depth apparent depth relationship as well. You know, you could have looked upon it that way too, right? So you could have said same thing it would have been. I mean, one could have imagined the whole thing like this. So if this was an object being viewed from air, then this would have been its image, because the ray of light would have gone this way and would have got refracted like this. That means because of an eye in air would perceive I1 to be the object, right? It would not perceive I2. So then this is my real depth, h, and this is h minus 5, the apparent depth. So h and h minus 5 could also be looked upon as real depth, apparent depth kind of situations. So see, same thing you will get. H by h minus 5. Very clearly, they must be separated by a factor mu. H and h minus 5 must be separated by a factor mu. H is bigger than h minus 5. So h must be mu times h minus 5. 4h minus 3h, h is 20 centimeters. Either way you want to look at it, your choice. Got me? You should be very transparent about these ideas. You should be able to see it. Right? Are you all there with me? Do you understand this? Because we use these in such a repetitive manner. You should understand the fact about reversibility of light. That means rays of light coming at I1, eventually converging at I2. Reversibility of light means if there was an object here, then if this was an incident ray, this would have been the refracted ray, and I1 would be where the object would be perceived by an eye in air. So then this length and this length are real depth, apparent depth. Right? If this was the real depth h, then h minus 5 would be the apparent depth. So h and h minus 5 would be separated by a factor mu. Always. Yes or no? Are you all okay with this? Let's move to the next problem. Were you able to get it right independently? All of you? With the ideas being very clear, because it's the same ideas used in different problems, right? All right, problem number 2 then. Is about a ray of light incident upon one face of a prism. This is a prism of angle A less than pi by 2. In a direction perpendicular to the other. This is an incident ray, and if you produce its direction, it's perpendicular to this other face. That's how it's incident, right? This is an incident ray. It would have hit the other face normally. Now, this is the normal at the point of incidence. This is the normal at the point of incidence. This is the refracted ray. This is the refracted ray, right? And this is the normal at the emerging face, and we don't want this to emerge. That means we want this angle theta to be greater than theta c, say. For it to not emerge, we want this theta to be greater than theta c, the critical angle. Yes or no? Between the pair of media, yes or no? Right? That's when it will fail to emerge. This is how it's going to happen. Now, if this angle is A, this is 90 minus A, right? This is also 90 minus A, and therefore angle of incidence is A. Angle of incidence is A? Yes or no? This angle is A. Now, at this point, realize that if this is theta, this is going to be A minus theta? Yes or no? This angle is going to be A minus theta. Right? Apply Snell's law at this point. Apply Snell's law at this point. Sine A is mu sine A minus theta. Yes or no? Yes or no? Now, if theta is more than theta c, then minus theta would be less than minus theta c, or a minus theta would be less than a minus theta c, yes or no? And therefore sine of a minus theta would be less than sine of a minus theta c, yes or no? So this sine a, which is this number is less than mu of sine a minus theta c. I don't want mu to stick around. I don't want mu to stick around. Now sine theta c is what? 1 by mu? Sine theta c is 1 by mu. So replacing mu by 1 by sine theta c. Sine a sine theta c, right? Replacing mu by 1 by sine theta c is less than sine, expanding this, sine a cos theta c minus sine theta c cos a, yes or no? Right? Dividing by sine a sine theta c both sides. Dividing by sine a sine theta c both sides, 1 less than cot theta c minus cot a. Is this what we are seeking to find? In a limiting case, you can say greater than or equal to for a limiting situation when theta just about becomes equal to theta c. That's a limiting state, right? Got me? You got this right independently? All of you? No? Close? The fun about optics is it's more of geometry. Huh? That also was not taught properly, yaar. Even if that was taught properly, na, it would have been right. All right, number 3 then. So we are now talking of a prism. We are now talking of a prism with refracting angle 90 degrees, right? This is angle A of the prism, 90 degrees. Gamma is the angle of minimum deviation. Gamma is the angle of minimum deviation, and beta is the deviation where at grazing incidence. Gamma is the angle of minimum deviation. So let's look at the state of minimum deviation. Now what transpires in a minimum deviation? Angle of incidence is equal to angle of emergence, isn't it? For minimum deviation, recall I must be equal to I prime, and this must also be equal, R must be equal to R prime, right? If this is R, then R must be equal to R prime to maintain mu, and this plus this is A, this plus this is A. That means each of these will be equal to pi by 4. Each of these will be equal to pi by 4, yes or no, right? See, R plus R prime is A. Angle of the prism is given to be 90 degrees, and R equal to R prime, because I equal to I prime, so R equal to R prime in a prism, each will then be equal to pi by 4. What do you say? Right? No? What's the deviation? I plus I prime minus A. That's a deviation. Gamma is given to be the angle of minimum deviation. So minimum deviation gamma is I plus I prime, that is 2I minus A, Yes or no? So I then is pi by 4 plus gamma by 2. Yes or no? I can apply Snell's law at this point. Sin I, that is sin pi by 4 plus gamma by 2 is mu sin R. Sin R is pi by 4. Yes or no? Sin A cos B plus sin B cos A. This gives me 1 by root 2 will get cancelled from both sides. Mu then is sin gamma by 2 plus cos gamma by 2. Yes or no? Expanding. Sin A cos B plus sin B cos A. 1 by root 2, 1 by root 2 will get cancelled. So sin gamma by 2 plus cos gamma by 2. Right? That's one. The second thing that is given is beta is the deviation. Beta is the deviation when this ray of light is incident at grazing incidence. That means when this is approximately 90 degrees, when this is slightly less than 90, if this is 90, then this will become critical, theta c. When this is 90, this will become theta c. Yes or no? Right? And when that happens, the deviation is given to be beta. Yes or no? Right? That means the second case, grazing incidence, roughly 90 degrees. This eye is roughly 90 degrees. We'll take it to be slightly less than 90 degrees. This is roughly 90 degrees. Close to 90 degrees. This is grazing incidence. This is grazing incidence. Why do I take it slightly less than 90 degrees actually? For calculations, I'll take it as 90, but slightly 90. Otherwise, the ray would have just gone like this if it was 90. Right? So I take it just slightly less than 90 so that it could find its way into the prism. And if it is slightly less than 90, then this would be critical, theta c. Right? This would be the emergent ray. Yes or no? Clear? Now, suppose this angle is I. I deviation beta is given by what? Sum of this angle plus this angle minus A. A is 90 degrees, right? A is 90 degrees. I plus I prime minus A. That's the deviation. So 90 degrees plus I minus 90 degrees. That means this angle I, beta must be equal to I. Beta must be equal to I. Yes or no? Beta is equal to I. That means this angle is beta. And this angle is A minus theta c. That is 90 minus theta c must be this angle. Right? Because this plus this is this A. Right? So this angle is 90 minus theta c. Right? Now I can apply Snell's law at this point. Sin beta would be mu sin 90 minus theta c. Right? So if I apply Snell's law at this point, mu of sin 90 minus theta c is equal to sin beta, which means I get mu cos theta c equals sin beta. Yes or no? Mu cos theta c sin beta. Now, this is the physics of the problem, right? Now let's look at the algebra required. Let's look at the algebra required. What is required? Do you all understand everything that I have communicated so far? Now let us see what is required. We want to show, can I just remove the clutter from here? We want to show number one, sine gamma is sine squared beta. We want to show sine gamma is sine squared beta. First of all, let me eliminate cos theta c. Cos theta c, let me eliminate from this. This is mu squared into cos squared theta c. That means 1 minus sine squared theta c is sine square beta. Yes or no? Mu square cos square theta c, which is 1 minus sine square theta c, is sine square beta. But sine square theta c is 1 by mu squared, isn't it? Sine theta c is 1 by mu. So on multiplying, I end up getting mu squared minus sine square theta c 1 by mu squared minus 1 is sine square beta. Yes or no? So now we have these two constitutions. We want to show that sine gamma is sine square beta. Very simple. If I square this, square equation 1, you end up getting mu squared equals sine square gamma by 2 plus cos square gamma by 2, which is 1, plus 2 sine gamma by 2 cos gamma by 2, which is sine gamma, 2 sine gamma by 2 cos gamma by 2, which is sine gamma. So mu square on squaring is 1 plus sine gamma. When I square this, sine square plus cos square plus 2, right? And mu squared minus 1 is sine gamma. Hey, but what is mu square minus 1? That's sine square beta. Mu squared minus 1 is sine square beta. That's the first part, right? Now, what else is required? We want to show cos gamma is mu cos beta. We want to show cos gamma is mu cos beta. Right? Now cos square gamma is what? 1 minus sine squared gamma. Because I have sines, that's why I converted into sines. Sine square gamma. Sine square gamma is sine to power 4 beta. Sine square gamma is sine to power 4 beta. So now I have brought beta in place, which is 1 minus sine square beta into 1 plus sine square beta. Right? 1 minus sine square beta, cos beta, good enough for us. Cos square beta, right? So this is cos square beta, 1 minus sine square beta, and 1 plus sine square beta. What is 1 plus sine square beta? Come back to one of the equations that we had written. 1 plus sine square beta, what would that be? 1 plus sine gamma. Sine square beta is sine gamma. So 1 plus sine gamma, and sine gamma could have been written as mu squared minus 1 is sine square beta. Sine gamma, is it? 1 plus sine gamma is sine square beta is sine gamma. This is mu square minus 1 is sine square beta. Okay, right from here, mu squared minus 1 is sine square beta. Check this out. Oh, look at this equation. Mu squared minus 1 is sine square beta. Just got lost with so many things. Mu squared minus 1 is sine square beta. So 1 plus sine square beta is mu square. 1 plus sine square beta is mu square. Right? So this is mu square. So cos gamma is mu cos beta. Cos gamma is mu cos beta. Yes or no? Got me? So cos gamma is mu cos beta, etc. Did you get this right independently? All right, let's look at problem number 4 then. we have a thin converging lens. We have a thin converging lens, refractive index mu2, placed just outside the plane surface of water. This is the surface of water, and just outside the surface of water, just outside the surface of water, we have this lens made of material of refractive index mu2. Now it's placed in air, essentially placed in air. There is an object O, let's say at a distance u from the lens, and it is found that the image of the source, this is the source, image of the source is formed at a distance x from the surface of water. That means almost from the lens. It's a thin lens. That's case one. That's case one. Now, what would it mean? Let's deal with this first. Let me write. So, if R1 and R2 are the radii of curvatures of the two bounding faces, this is focal length. This is a lens in air now. And its refractive and its focal length in air, 1 by f, is, it's made of material of refractive index mu2, is it? Mu2. Mu2 minus 1 into 1 by R1 minus 1 by R2. R1 and R2 are algebraic radii of curvature of the two bounding faces. Yes or no? And the sign is built into this, because R1 and R2 are algebraic, there is sign already built into this. Now think of it. Image distance, all right. X, V is minus X. V is minus X. But what about U? What about U? Before a ray of light hits the lens, it has to get refracted from the water surface. It has to get refracted from the water surface. So if this was an object O, even before it could emerge, for an observer, in this case the observer is the lens. The lens would not find the object to be at O. From the perspective of the lens, this ray of light coming from O, before it is incident on the lens, it seems to be coming not from O but from O prime. But from O prime. Yes or no? The lens is in air. The lens is in air, right? The object appears to be raised. For the sake of the lens which is in air, it's like an eye in the air. The ray of light which is incident on the lens doesn't seem to be coming from O but seems to be coming from O prime. So for the sake of the lens, the object distance is not U, but this is U. The object distance is going to be this. This would be the object distance, which is U by mu1. Mu1 is the refractive index of water. Yes or no? So the object distance for the lens is not U, but is U by mu1. The image distance is X. Since it's in air, this is the focal length of the lens in air. So I can apply for this situation where U is U by mu1, V is minus X, and F is this. I can apply 1 by V minus 1 by U equal to 1 by F for the lens for this situation. So 1 by V means minus 1 by X minus 1 by U. 1 by U means again positive U by mu1 because it's measured in this direction. So minus 1 by U by mu1 equals 1 by F, which is mu2 minus 1 into 1 by R1 minus 1 by R2. Yes or no? For this case, do you all understand this? If there is a doubt, ask me, because these are the only things that you need to understand in geometrical optics and nothing else. Suraj? Nahin? Sure? So that's for the first case when the lens is just above water. The object doesn't seem to be at O, it seems to be slightly raised. Right? Now the second case, the lens is placed just inside water. The lens is placed just inside water, and the image is formed at a distance x prime from the surface of water. So when it's placed just inside water, the object distance remains u only, right? But the focal length of the lens would be focal length in water. That mu minus 1 would be mu of the material of the lens with respect to water. You know what I'm saying? And then the image is formed in air at a distance x prime from the lens. That's the second case. Let me write 1 by v minus 1 by u equal to 1 by f for the second situation when the lens is just immersed inside the water. Clear? So this equation done. I can remove the clutter from there, right? Look, this is what happens. This is the lens. Very thin. So the object distance remains u only approximately for the sake of the lens, right? The focal, now what would happen is, if there was only water surrounding the lens, if there was, above this also there was only water, what would happen? If this was the object, this was a ray of light, this would have been its image, if there was only water. Then the image distance v, algebraic image distance v, would have been given by what? 1 by v, right, minus 1 by u. If it was water all the way, right, then the image distance, if this was not air but this was also water, 1 by v minus 1 by u equals 1 by the focal length of the lens in water. 1 by the focal length of the lens in water. Now how does one compute the focal length of the lens in water? Mu of the material of the lens, which is 2 with respect to 1, minus 1 by 1 by r1 minus 1 by r2. This is the geometrical factor which does not change. This is mu 2 by mu 1, right? So this is mu of the material of the lens with respect to the surrounding water, mu 1, minus 1 into 1 by r1 minus 1 by r2. r1 and r2 are algebraic. So the sign is built into this, right? So then the image distance v, if there was only water surrounding, 1 by v minus 1 by u will be equal to this. Yes or no? But alas, that's not how it happens. This ray of light which is converging at I, if there was no refraction from the water surface, if there was refraction only from the lens, it would have converged at I. But what happens? This ray of light, which would have sought to converge at I, it would have liked to converge at I, right? Because of the water surface, it'll go away from the normal. See, this is how it would have gone. If there was only water, this ray of light would have converged like this. But it encountered a water surface, it would have liked to converge to I, right? This is V. Instead, it'll go like this. It'll go like this, yes or no? It's going from denser to rarer medium, so it'll bend away from the normal. It'll go like this. It'll go this way, I prime. It'll eventually converge at I prime. It would have converged to I if there was water. But because of this interface, it'll bend away from the normal. Denser to rarer medium, it'll bend away from the normal and it converges at I prime. Yes or no? And this I prime is known to be at a distance x prime. This I prime is known to be at a distance x prime. Yes or no? Do you all understand this? Huh? This is x prime. This is x prime. And therefore, V, this length is mu x prime, mu 1 x prime, yes or no? Because this and this must be separated by mu of water, yes or no? So that means this must be mu 1 x prime. So this V can be replaced by mu 1 x prime. This V can be replaced by mu 1 x prime, yes or no? I hope you understand this. I can redo this. I can rewrite this to explain this further. Shall I explain this one more time? No. See, this ray of light would have liked to converge this way, right? But the water surface here would cause it to bend away from the normal. It converges at I prime instead, right? So this is given to be x prime. So this must be mu 1 x prime. So V, this was V. V must be mu 1 x prime. This is the equation as if there was water all around. So V, if there was water all around, would have been mu 1 x prime. So this V can be replaced by mu 1 x prime, yes or no? Minus mu 1 x prime, in fact.
According to the question, the lens is just immersed into water. So the upper surface of the lens should be at the surface, should be at the water surface.
No, they would, no. I mean, when they say just immersed inside, means, you know, there is a layer of water that will participate in refraction. No matter how thin it is, there would be a layer of water that would participate in a subsequent refraction. This is what it means, right? So this V must be, this V algebraically is negative, because so minus mu 1 x prime, minus mu 1 x prime. So replace this V by minus mu 1 x prime. That's for these. That's the constituent equation for the second case. I will have no problems explaining this again, because all of geometrical optics would be about this only. So if these ideas are shady, are not properly set into you, then you know you'll face the same stumbling block time and again. Do you understand whatever I've done here? Huh? And why negative? Because it's measured in the same direction as incident. So minus mu 1 x prime, this length V. एयर का तो वन है देवी, वाटर का ही होगा, है ना? Because if there is a ray of light from water to air, so it goes this way, so it has to be that of water, isn't it? Okay, so then we have everything set for us. That's equation 2. What you want to do is multiply this by mu 1. So if you multiply this by mu 1, then minus 1 by x prime minus mu 1 by u equals mu 2 minus mu 1 into 1 by r1 minus 1 by r2. And obviously you want to eliminate, so subtract. Do a subtraction of these two. So when you subtract, you get minus 1 by x minus 1 by plus 1 by x prime equals, and this will get cancelled. So that will be mu 1 minus 1 into 1 by r1 minus 1 by r2. Right? When you subtract, this is what happens. This minus this, right? And 1 by r1, see, f is the focal length in air. So 1 by f is mu 2 minus 1 into 1 by r1 minus 1 by r2. r1 and r2 are algebraic. So 1 by r1 minus 1 by r2 would be 1 by f, and this mu 2 minus 1 will come in the denominator. So this is mu 1 minus 1, eliminating this by f 1 by mu 2 minus 1. This is what happens. So 1 by x prime minus 1 by x is this. F is the focal length of the lens in air. Did you get it right on your own? 1. But do you understand this now? Pakka na? The fifth problem of the sheet is about an arrangement of the following kind. There is an equiconvex lens whose radius of curvature of the two bounding faces is 32 centimeters. 32 centimeters is the radius of curvature of the two bounding faces. The mu of the material of the lens is given to be 1.5, and one side is silvered. First of all, let me obtain the equivalence of this lens. The equivalent of this would be a mirror. So first things first, if the radius of curvature of the two bounding faces is 32 centimeters, then in our scheme of things, the focal length of this lens is going to be mu minus 1 by R1 minus 1 by R2. 1 by R1 is minus 1 by R, 1 by R2 is minus 1 by R. So minus 2 by R, R is the radius of curvature of the bounding faces, yes or no? R1, which would be minus R, R2, that will be R. So minus 1 by R, minus 1 by R, I hope you understand this, right? Mu minus 1, 1 by R1 minus 1 by R2. Now, if R is the magnitude of the radius of curvature of the two surfaces, then the R of this would be minus 32 minus R. R2 in this direction would be plus R. So minus 1 by R, minus 1 by R, minus 2 by R, where R is the radius of curvature. So minus 2 by R, right? So R is given to be 32. So the focal length of the lens alone, if there was no mirror, of the lens alone, the focal length would have been minus 32 centimeters. It's a converging lens. Now, the radius of curvature of this is 32 centimeters. So for the mirror, just the mirror part, focal length of this last surface, which is a mirror, will be 16 centimeters. And it's a converging device, 16 centimeters. Now, for the combo has focal length, the whole combo will be like a mirror with focal length 1 by f combo is 2 by the focal length of this device. This is a converging device. So instead of taking minus 32 centimeters, I'll take this as 32 centimeters. Yes or no? So 2 by 32 plus 1 by fm. 1 by fm means 1 by 16. Again converging device. So 1 by 16. 1 by 16. So 2 by 16. 1 by 8. That means this whole thing behaves like a mirror with focal length 8 centimeters means a concave mirror with focal length 8 centimeters. So can I just wipe this off and replace it by its equivalent mirror? A concave mirror of focal length 8 centimeters. So this whole thing is like a concave mirror with focal length 8 centimeters. Focal length 8 centimeters. Therefore, the radius of curvature of this is 16 centimeters of this. Right? This behaves like a concave mirror with focal length 8 centimeters and therefore radius of curvature 16 centimeters. Now, what is done is a second convex lens of focal length 24 centimeters. There is a convex lens here with focal length 24 centimeters. Is placed at a distance x from this unit. an object placed 14 centimeters from this arrangement, right? There is an object O which is placed 14 centimeters from this arrangement. 14 centimeters from this arrangement, right? This is the whole thing. Now what is it that we want? We want the image of O to coincide with O. That's what we want. Now how's the final image of O formed? The final, see, first there is refraction from this lens commensurate with 1 by V minus 1 by U equal to 1 by F, right? The image of this will serve as the object for this, right? An image of this is, of that object, virtual object, is formed by reflection from the surface, 1 by V plus 1 by U equal to 1 by F. That will form an image, right? Now, the rays on coming back hit the lens, they undergo refraction at the lens, but refraction at the lens, the image formed by this will serve as an object for refraction on the lens, and then after the subsequent refraction from the lens, a final image is formed. And we want that final image to coincide with O. Now, what is it that is actually required? Rays of light after having undergone refraction from the lens must be incident normally on the mirror, right? Now for this ray to be incident normally on the mirror, this is a ray of light and you want it to be incident normally on the mirror. So if it is incident normally on the mirror, it will retrace its path. Reversibility of light, it will retrace its path and the final image would be formed at O. Yes or no? Which means if this ray is incident normally on the lens, or on the mirror, that means when you produce it, it must seem like coming from the center of curvature of the mirror. It must seem like coming from the center of curvature of the mirror. Yes or no? When would this ray be incident normally on the lens, on the mirror? When you produce it, it will seem like coming from the center of curvature of the mirror, right? Which means this C, that means the ray which is incident on the mirror seems to be coming from C. That means this C must be the image formed by refraction from the lens. If O is the object for the lens, then C must be its image, because after refraction the ray of light seems to be coming from C. So C must be the image for the object O. Yes or no? For refraction from the lens. Are you there with me? And this C is 16 centimeters from the mirror because the radius of curvature of the mirror is 16. So the image distance from the lens is 16 minus x. This is x units. Yes or no? So this must be 16 minus x. The image distance. For the object O, the image distance from the lens is 16 minus x for refraction from the lens. And the object distance, again, as you can see, this object is 14 centimeters from here. This is x units. So the object distance is 14 minus x. Yes or no? Then for refraction from the lens, I can apply 1 by V minus 1 by U equal to 1 by F, 1 by V. Now V measured in this direction, so positive, opposite to the direction of the incident ray. So 1 by 16 minus x minus 1 by U, which is 14 minus x, measured opposite to the direction. This is refraction from the lens, right? 1 by 14 minus x is 1 by F. F is minus 24 for the lens. So minus 1 by 24. Yes or no? So minus 2, so 48 equals x minus 16 into x minus 14, x squared minus 30x plus 16 into 14 minus 16 minus 2. Minus 30x 176 is 0, 122 8. If I have not made a mistake, then this is what it should be. So x can be 22 or 8. Now 22 is not possible, because if x were to be 22, this lens would have been to the left of O, which is not the case. So x must be 8 centimeters. X must be 8 centimeters. All's good, right? Can I wipe this off? So this was 5th, right? Let me look at 6th. Were you able to get it right on your own? No? But you're understanding all these sign conventions and you know the basic tenets of geometrical optics, right? I mean, geometrical optics essentially is very simple. You know, just a handful of ideas and used again and again. So once you get a hang of those ideas, you know, by means of a few problems, then you will realize it's repetition of the same thing. So there is a ray of light falling on a glass sphere made of material of refractive index √3. Your attention please. There is a glass sphere made of material of refractive index √3. Right? This says the center of the sphere. There is an incident ray. There would be refraction from this surface. Then there would be refraction from this surface. This is an incident ray. There would be an emergent ray, and there would be a refracted ray, and there would be an emergent ray. Now what they say is that if you produce the incident ray and if you produce the emergent ray, this is the emergent ray, they intersect at the same point. This is the emergent ray. When the incident ray and the emergent ray are produced, they intersect at the same point P on the glass surface. Right? That's given. We want to draw the ray diagram and find the value of the angle of incidence. Clear? Do you understand the problem? Okay. This is an incident ray. The radius is always the normal at the point of incidence. Right? And this must be the refracted ray then. RR. Right? This must be the normal here. And this must be the emergent ray, bending away from the normal. Yes or no? This is the ray diagram then? I want to find I. I want to be able to find I. Very clearly, what is this angle? R. Angle of, this is R. Right? I can apply Snell's law here. Sin I is root 3 sine r? Yes or no? Now, if this is right, I hope you understand this is r, this is also r, isosceles triangle. What must this angle be then? I, obviously, to preserve mu. If this is r, then this must be I. I want to find another relationship from the geometry that would connect r and I. And so that I could eliminate r and solve for I. This is what I want to be able to do. Clear? This angle is pi minus 2r, isn't it? So this angle must be pi plus 2r, 360 degrees and all, right? This angle is I minus r, this angle is I minus r, right? Isn't it? I minus r, I minus r. So this angle must be pi minus twice I minus r. Yes or no? Pi minus twice I minus r. Angle at the center will be twice the angle on the circumference. Right? That means this angle must be twice this angle. Isn't it? Angle subtended by this arc at the center, which is this, must be twice the angle that it subtends on the circumference. Right? So pi plus 2r then, which is angle at the center, is twice right? So this gives me 4 into I minus r plus r equals pi, right? Minus, have I made a mistake here? Pi plus 2r, right? 2r. So 4i minus 2r is pi. Or I then is pi plus 2r, or I want to replace r. R is 4i minus pi by 2, which is 2i minus pi by 2. 2i minus pi by 2, that's r, right? So r I can replace by 2i minus pi by 2, 2r minus pi by 2. So sine I is root 3 sine 2i minus pi by 2, which is minus cos 2i, which is minus cos 2i. Yes or no? Cos 2i again in terms of sin I is 1 minus 2 sine square I. 1 minus 2 sine squared I. I use the minus sign. 2 sine squared I minus 1. That's sin I. 2 root 3 sine squared I minus sin I minus root 3 is 0. Right? I won't take minus here because this will become negative. Sin I is not negative, right? So I take plus 5 plus 1 6 by 4 root 3. I reject the minus sign here. So sin I is 6 by 4 root 3. 3, so root 3 by 2. Sin I is root I is such that sin I is root 3 by 2. Clear? If I have not made a mistake, then this is what it should be. So x can be 22 or 8. Now 22 is not possible, because if x were to be 22, this lens would have been to the left of O, which is not the case. So x must be 8 centimeters. X must be 8 centimeters. All's good, right? Can I wipe this off? So this was 5th, right? Let me look at 6th. Were you able to get it right on your own? No? But you're understanding all these sign conventions and you know the basic tenets of geometrical optics, right? I mean, geometrical optics essentially is very simple. You know, just a handful of ideas and used again and again. So once you get a hang of those ideas, you know, by means of a few problems, then you'll realize it's repetition of the same thing. So there is a thin converging lens of focal length 1.5 meters such that the y-axis, such that its optical center coincides with the origin. Optical center coincides with the origin, is placed along the y-axis. That means this must be the y-axis. This therefore must be the x-axis. A small source of light is placed at -2, 0.1. -2 means 2 meters to the left, and 0.1 meters. This is a small source of light. 2 meters. You could look upon this as an extended object of 0.1 meters. You could look upon this as an extended object of size 0.1 meters. Where should a plane mirror inclined at an angle theta be placed such that tan theta is 0.3 with the vertical? Maximum intensity is obtained at a point y equal to 0.3 meters. Also find the x coordinate of the final image. So what we are seeking to do is, we are actually dealing with a refraction from the lens, a reflection from the mirror, and then the final image. And we want the final image to be formed 0.3 meters at y equal to 0.3 meters. How must the mirror be placed so that this could be accomplished, right? The mirror is placed at an angle given by theta with the vertical, tan theta is 0.3. But where exactly should it be placed so that the image is formed, final image, because you know, that will be a high intensity point. Wherever the final image is formed, that would be the high intensity point, bright point, all right? And we want that to be at y equal to 0.3, the final image after refraction from the lens and reflection from the mirror. Right. So first of all, forget the mirror. Forget the mirror for a while. If the object distance is 2 meters, focal length is minus 1.5 meters. Let me find the image distance if the mirror was not there, right? 1 by v minus 1 by u equal to minus 2 by 3, 1.5, right? So 1 by v, half minus 2 by 3, minus 1 by 6. So v is minus 6 meters. That means 6 meters to the right of the lens, that's where the image would be formed, right? So realistically, what is happening is, if this was the lens, if this was the object O of size, imagine this to be an extended object of size 0.1 meters, then the image of this object, is formed 6 meters to the right of the lens, and the magnification, as you can see, is 3. Right? 6 by 2, 3. That means the size of the image would be 0.3 meters. Size of the image would be 0.3 meters. Like I have mentioned to you, in my scheme of things, we will take magnification only for its magnitude. Alright, from ray diagrams, we will not look at the sign of M and determine whether an image is inverted or erect, real or virtual. We will do so by means of a ray diagram rather than depend on the sign of M. We will take M to be positive only. We now know if the object size is 0.1 meters, the image size must be 0.3 meters. Now think of it. Where would the image of S be formed? Think of a ray of light like this, parallel. Its focus is 1.5 meters, so it will pass through the focus, and 6 meters away from the lens, it will pass through an image of this would be formed. That means, the image is formed beyond the focus. The image is formed beyond the focus, which is 1.5 meters. And if it's formed beyond the focus, the image of S must be below the principal axis. Must be below the principal axis, yes or no? Because it's 6 meters away from the lens. And this is 1.5 meters. So it's formed beyond this. So if it is formed beyond this, then the image of S would be S prime and would be 0.3 meters, given the magnification. From the ray diagram, we'll figure out whether the image is virtual or erect. In this case, whether the inverted or erect. In this case, it's inverted from the ray diagram, because this is like this, it goes this way. Or you could have had a ray coming from the optical center, going this way and settling at S. Isn't it? Going undeviated from the optical center and settling at S. So it's below the principal axis. So image of this must be inverted and is of size 0.3 meters. Yes or no? I again warn you against choosing to obtain whether the image is erect or inverted based on the sign of M. I find this very shoddy and very spurious. From the ray diagram, we'll figure out whether it's inverted or erect. Another story, don't open the Pandora's box. I will be able to give you a lot of complications that may arise if I did that. Why not just draw ray diagrams effectively and obtain and get rid of all complications? It's as simple as this. Realize? So I know it's 0.3 meters. That is where, but what is happening is, well before it can mature to converge at S, it is intercepted by a mirror. It is intercepted by a mirror. And for the sake of that mirror, this S prime would be a virtual object. This S prime would be a virtual object. And its image, the image of S prime would be at S double prime, say, which is formed at y equal to 0.3. You know what I'm saying? So, essentially, this is the mirror which is placed somewhere. This is the mirror. The image of S is at S prime, which is y equal to minus 0.3. Right? This is the mirror placed at an angle theta with the vertical. Tan theta is 0.3. And the image of S prime is at S double prime. The image of S prime is at S double prime, which is y equal to, this is y equal to minus 0.3 actually. Minus 0.3. And this is y equal to plus 0.3, the final image. Yes or no? Now, S prime is the virtual object and S double prime will be its real image. Will be its real image, right? A plane mirror can form a real image, right? Will be its real image. And the line join, so this enjoy the object image relationship. Object and its real image. Virtual object and its real image formed by this mirror. Now, realize that the line joining the object and the S double prime, S prime. Line joining the object and the image is perpendicular to the mirror and is halfway between these two. Yes or no? This point P must be the midpoint of S prime and S double prime. Yes or no? The point where the line joining the object and the image intersect the mirror will be midway between S prime and S double prime. So if this is y equal to minus 0.3 and this is y equal to plus 0.3, that means this point P where the object and the image intersect, the line joining the object and the image intersect the mirror must be y equal to 0. That means this is the object, this is the image, and this line on this point on the mirror must be on the x-axis, Very good. You understand that, right? So which means this point is the only point on the mirror which lies on the x-axis. This is the only point on the mirror which lies on the x-axis, and it must be halfway between S prime and S double prime. So which means the line joining the object and the image must be here. Y of this plus y of this by 2 must be y of this, which is 0, which is the point on the x-axis. Yes or no? Clear? And this is perpendicular to the mirror. Line joining the object and the image is perpendicular to the mirror. Clear? Very good. Now, this angle is theta. This is 0.3 meters. This also is 0.3 meters. This is theta. This is 90 minus theta. So this must be theta. Right? Tan theta is 0.3. Tan theta is given to be 0.3. That means if this is the point P, this is M. Would you mind believing that MP must be 1 meter? Yes or no? MP must be 1 meter. Yes or no? See, if tan theta is 0.3, that means this by this. And if this is 0.3, then MP must be 1 meter. And PQ, these two triangles are similar, are congruent actually. This triangle is congruent to this triangle. So if this is 1 meter, this must also be 1 meter because this is 0.3. Same tan theta. So this is 1 meter, 1 meter. So far so good, right? Which means now we are all there. This was the original lens L. This was the lens L, right? This is S prime. This is S double prime, right? This distance is given to be, is found to be 6 meters from the lens, and this is 0.3. This theta, tan theta is 0.3. This is 0.3. Yes or no? And since tan theta is 0.3, like I said, this is 1 meter. This is also 1 meter. This length is 1 meter. This length is also 1 meter, right? That means, and this whole thing, this is 6 meters. So the point where the mirror intersects the x-axis is 5 meters. The mirror must be placed like this. The mirror must be inclined at an angle theta, intersecting the x-axis 5 meters from the lens, right? And the position of the final image. This is the position of the final image very clearly. This is 5 meters, this is 1 meter, so this is 4 meters. So the coordinates of the final point would be 4, 0.3. Yes or no? 4, 0.3 is the position of the final image. Yes or no? Are you confused? Very little of optics. Right? Huh? Shall we proceed then? So here we have a medium with mu equal to root 2. And this is vacuum, that is air, for all practical purposes, right? A ray of light is incident at this. Obviously, it passes from a denser to a rarer medium. This is mu equal to 1, so it will bend away from the normal. We want to find the range of I. We want to be able to find the range of I for which the deviation suffered by the ray has a unique value. That means that deviation is obtained only for that angle of incidence and for no other angle of incidence. We want to be able to find the range of I for which the deviation obtained is unique. That means no other value of I gives me the same deviation. Now, you might be tempted to believe, hey, it's trivial. Maybe, obviously that's the case, but actually not. That's not the case. See, there are two regimes for this situation. Initially, when you go on increasing I, as you go on increasing I, R will also go on increasing, right? And as you can see, the deviation here would be this angle, I minus R. We can show that as I increases, deviation increases. Deviation goes on increasing as I increases. We can show that explicitly. Now, so initially there is refraction. Initially there is refraction for which the deviation is I minus R. This will not go on forever. Eventually I will become critical angle for the pair of medium, and when I becomes critical angle for the pair of medium, when I becomes theta c, then there would be this as the refracted ray, right? And that means angle of refraction will become 90 degrees, right? So at this point, delta when I is theta c is how much? Okay, first of all, what is sine theta c? 1 by mu here. So theta c is pi by 4, right? And when theta c is pi by 4, that means when I is pi by 4, R becomes pi by 2. Yes or no? So this should be R minus I. Isn't it? R is more than I. This angle is R minus I. Just to fix this, R minus I, right? So when theta c is this, that means when I is pi by 4, what is R? When I is pi by 4, which is critical angle of refraction must be 90 degrees because this is critical angle. R is pi by 2. R is pi by 2, right? So the deviation when the angle of incidence is pi by 4 is R minus I, which is pi by 2 minus pi by 4, which is pi by 4. When I was 0, deviation was 0, because if I is 0, the ray will go undeviated like this. When I becomes critical angle pi by 4, then the deviation becomes pi by 4. And from I equal to 0 to I equal to theta c, deviation will continuously increase. It will not be linear, it's a non-linear increase of deviation that will take place. Deviation as a function of angle of incidence. When I is 0, deviation will be 0 because R will be 0. When I becomes equal to critical angle, then deviation becomes pi by 4. It's monotonically increasing. Now, what happens beyond this point? When I becomes greater than pi by 4, there is going to be total internal reflection, yes or no? So this is the refraction regime. This is the refraction regime. From I equal to 0 to I equal to critical angle, deviation increases from 0 to pi by 4. Now beyond this point, there will still be deviation, but that would be at the behest of reflection, not at the behest of refraction. Yes or no? When I becomes greater than theta c, when I becomes greater than theta c, this is the incident ray, this is I, then there is going to be total internal reflection. There is going to be total internal reflection for I more than pi by 4, for I more than pi by 4. And then the deviation is not given by r minus I. See, what 2I? Pi minus 2I. This is I, this is I. This is pi minus 2I is the deviation. Yes or no? The ray would have gone like this, but now it's going like this. So this is the deviation, pi minus 2I. 2I would have been if this angle was I. If this angle was I, then that would have been 2I, the deviation. When I would have been the grazing angle, not the angle of incidence. So if I is the angle of incidence, then the deviation produced in reflection is pi minus 2I. Now if I is increased, so the deviation produced now in this regime is pi minus 2I. And it's linearly varying with I. Right? Limit delta as I tends to pi by 4 from the greater than pi by 4 side, right? In this case, I is greater than pi by 4 is pi minus 2 into pi by 4, which is pi by 2. That means the right hand, that means there is discontinuity in deviation, because the left hand limit of delta as delta tends to pi by 4 is pi by 4, but the right hand limit of delta is pi by 2. That means there is an abruptness, there is discontinuity produced by the deviation function. The deviation function produces discontinuity at I equal to theta c. Yes or no? Do you understand that? And then the good part is that for total internal reflection, delta versus I would be a straight line with negative slope, decreasing therefore. With the right hand limit, this is a kink in the function, and this is pi by 2. Yes or no? This turns out to be pi by 2, right hand limit, and then it linearly decreases. Yes or no? This is what happens, right? Pi minus 2I. This is delta equal to pi minus 2I. Now, notice that if I was lying between 0 to pi by 4, say some I lying between 0 to pi by 4, there is a deviation produced here which is like this, but the same deviation is produced in the reflection domain also, isn't it? There is some other value of I, say I prime, which is producing the same deviation. That means I from 0 to pi by 4 is not producing deviations uniquely. There are other values of I also that produce the same deviation. Do you realize that? So we don't want such I's. In contrast, if I lies between pi by 4 to theta, see, if I lies between pi by 4 to some theta, then for these I's, these are the deviations produced. For these I's, these are the deviations produced, and they are unique. These deviations are not produced for any other I. Yes or no? So what we want is I to lie between pi by 4 and theta. I to lie between pi by 4 and theta. Then the deviations produced would be these, which would be unique and will not be produced for any other value of I. Right? So I need to find theta. Then the required range of I will be greater than pi by 4 and less than theta. That would be the range of I. Yes or no? Do you all understand that? Very good. So now that's simple. This delta is pi minus 2 theta. Pi minus 2 theta, isn't it? Pi minus 2I, pi minus 2 theta, which is equal to pi by 4. 2 theta is 3 pi by 4, or theta is 3 pi by 8. Theta is 3 pi by 8. Yes or no? So if I lies between pi by 4 to you can include this as a limiting case, less than or equal to 3 pi by 8. Then the deviations produced would be unique, and no other values of phi will produce the same deviation as the deviation produced by these angles of incidence. Yes or no? Sure, na? And what I want you to check is a statement which I made, but I didn't qualify enough. I said if I is increasing, R is also increasing, but R minus I will also increase. That means what you want to show is, first of all, sin I, root 2 sin I is sin R, right? Deviation is R minus I. What you want to show is d delta di to be positive. What is d delta di? D delta di would be dr di minus 1. You want that to be positive? That means you want dr di to be greater than 1. Differentiate this with respect to I. You will be able to get dr di greater than 1. And that will establish that R is increasing with I. You can check that independently. It's an easy thing to show. Got me? You know what I'm saying? Delta is R minus I. I want to show that d delta di is positive. That means dr di minus 1 is positive. Dr di minus 1 will be positive if dr di greater than 1. If you differentiate this with respect to I, you will get the value of dr di. And you will be able to establish that dr di is indeed greater than 1. So there is an isosceles glass prism . Isosceles glass prism means this angle is equal to this angle, and with this face silvered. A ray is incident on the other face, normally incident on the other face. This is the other face which is non-silvered. This angle is A. If it is incident normally, it will go undeviated. It gets reflected from this, and then it is known to come this way. This is how it is. We want to find the total deviation produced. We want to find the total deviation. That means the angle between the incident ray and the emergent ray. You know what I'm saying? This is 90 degrees. This is A. This angle is, this is an incident ray here. This is 90 minus A. Yes or no? This angle is 90 minus A. And this is the reflected ray, so this angle must also be 90 minus A. Right? And therefore, this angle must be 2A. Yes or no? This is 90 degrees, so this must be 90 minus 2A. Right? This is reflection from this, so this is also 90 minus 2A. Right? This is 90 degrees and this is 90 minus 2A. That means this angle must be 2A. This angle must also be 2A. 2A plus A, 5A is 180 degrees. So A is 36 degrees. Now the deviation. So far so good, right? Now, this incident ray and this zero deviation here. The total deviation would be deviation here plus deviation here plus deviation here plus deviation here. That will be the algebraic deviations, right? I'll take all clockwise deviations positive, all anti-clockwise deviations negative, right? So delta would be zero deviation here, right? Plus the ray would have gone this way, but now it goes this way. Deviation is twice the grazing angle, clockwise, right? Twice of this angle, twice of 90 minus A would be the deviation here, clockwise. Now, for this second case, the ray would have gone this way, but now it's going this way. Anti-clockwise deviation, so negative. That means, and the magnitude of the deviation would be twice this angle, but of opposite sign, right? So minus twice of 90 minus 2a, that's the deviation. So that is 4a minus 2a, 2a is the deviation. That is 72 degrees is the deviation produced. You got it right all by yourself? So first of all, the whole arrangement consists of an equiconvex lens L here, mu equal to 1.5, and whose focal length in air is 40 centimeters. When this was not mirrored, the focal length of this was 40 centimeters, means minus 1 by 40 is mu minus 1, which is 0.5 into minus 2 by r. R is the radius of curvature of each of the bounding faces. Yes or no? Nahin? So r must be what? 40 centimeters. Each surface must be 40 centimeters, right? Now, if r is 40 centimeters, then the focal length of this combo, if this is mirrored now, the focal length of this combo would be what? 1 by f combo would be 2 by, again, it's a converging device. This is a converging device, so I will not take minus 40. I'll take plus 40. So 2 by 40 plus 1 by focal length of this. This is like a mirror whose radius of curvature is 40 centimeters. That means the focal length of this part is 20 centimeters. See, the radius of curvature of this bounding face is 40 centimeters. So focal length is 20 centimeters. It's a converging device. So plus 1 by 20 centimeters. So 1 by 20, 1 by 10. That means this behaves like a concave mirror of focal length 10 centimeters. This behaves like a concave mirror of focal length 10 centimeters. Yes or no? Right? Okay. Now come to the problem. There is like a concave mirror of focal length 10 centimeters. There is an object O placed at a distance A. There is a mirror here placed at a distance B. And what's given is there is an image formed by this and there is an image formed by this mirror, plane mirror, and there is no parallax between the two. That means the image formed by this and the image formed by this are at the same point, Not only that, if the transverse length of the final image formed by this is twice that of the image formed by the mirror. They are formed at the same point, but the image formed by this is twice in size the image formed by this. We want to be able to calculate A and B commensurate. Okay, forget everything, just come to the image per se. There are two images formed at I. There is an image I1 formed by the mirror, this concave mirror, and I2 formed by the plane mirror at the same point I. For the mirror, what's the object distance? A plus B, right? And the image distance therefore would be A plus B. Now for the combo, this was the combo. U is plus A, V is minus of A plus 2B, and F is 10 centimeters. F is 10 centimeters for this, yes or no? U is plus A, V is minus of this, and F is plus 10 centimeters for this. I can apply V plus 1 by V plus 1 by U equal to 1 by F, 1 by V, that is minus 1 by A plus 2B. A plus 2b plus 1 by A u equals 1 by 10, right? Now size of the object and size of the image formed by the plane mirror is the same, right? What's the magnification produced by this? Magnification produced by this is what? A plus 2b by A. That's the magnification produced. Yes or no? A plus 2b by A is the magnification produced. And what's the magnification? 2, isn't it? Is the magnification not 2? Right? So A is 2b or not to be? To be, right? A is 2b, plug in the value of A here, minus 1 by 4b plus 1 by 2b is 1 by 10. You can solve for b and then obtain A from these considerations. As simple as this, isn't it?